little while back, I was listening in on a design review for a device that was heading into its second iteration. The engineers leading the presentation kept talking about CAD-itis, CAD-itis, like maybe some of the features were much smaller than they were expecting them to be, or the mechanisms didn't work right. I'd never heard the term CAD-itis before, but I've definitely been dealing with this for as long as I've been doing this work. CAD, of course, creates this sort of artificial universe where everything is geometrically perfect. Remember our friend Plato? He would love it there. It's a fun place to be. Lots of us like it there. We don't mind spending many hours a day. It's a pretty good job. But you got to be careful because the CAD world will mess with you. It will hide problems from you. And in this video, I want to drill in on one category of those problems, okay? This is the problem of over-constraint. And this video is for all of us because we all feel the temptation of over-constraint. But it's especially for those engineers who again and again give in to that temptation or who relish in over-constraint. Those engineers who I say are addicted to over-constraint. All right, so let's get into it as we always do with some models and drawings. So here's an assembly of parts that will have one group of people saying, yeah, that looks just fine to me. While another group will be saying, no, don't do that. Now, just to run through it, this blue part here is like one end of a larger part. You can see I've got it kind of cut off there. And then the gray part is, we'll call it a brace, okay? And it's also cut off just around this little detail area. So this is really just to show how these two parts would go together. The really controversial thing with this has to do with how these two sets of screws, 4 up here and 4 down here, how they'll pull the gray part against the blue part in 2 different directions. I see people doing this when they expect to have forces in both of those directions and don't want to put the screws into shear load. Or maybe they have it in their head that they just want to create like a really sturdy bolted joint. But this is likely to be a frustrating assembly for anybody who has to put it together. Let's assume for a minute that these parts are both made really well. In particular, they're really super square in here. Which screws do I tighten first? The ones on the top or the ones on the side? Maybe I turn them all just until contact and then go back and torque them all later. Maybe I'm working in a pattern like I do with the lug nuts on my car wheels. Okay, it might work, or it might not be that great. Let's remind ourselves of how these screws work. As we turn them into the threaded holes, they will close the gaps between the gray piece and the blue piece. When they tighten, the screws will stretch a very small amount and will essentially become very stiff springs. That spring force results in preload and will generate friction at the joint between the gray piece and the blue piece. With screws like these, it can be a subtle distinction, not very much turning of the wrench at all, that can make the difference between loose and so much friction that you can't really move these parts at all anymore. Maybe I'm not telling you anything you all haven't already experienced yourselves. What happens if I cross that line with the screws on top, but I leave a little gap on the side? Maybe it's very small. Now I have no real preload on the side. All I'm doing is preloading the friction on the top joint. Maybe one day these parts will take a mechanical shock and the joint will slip. Then my side screws will be loose. There's another possibility that I close the gap down here by stressing the gray part, deforming it. Also not ideal. At the beginning of this example, I asked you to assume that these parts were made very square. But what if they're not? In this case, the gray part is a little more obtuse than the blue part. And you can see it has 2 positions it likes to be in. Always creating a gap on one side or the other. And aside from that gap, whatever's at the other end of this gray piece is going to have a really hard time getting into the right position, isn't it? Unless maybe your idea is that we're going to use these screws to somehow tune this thing into just the exact right position where it's supposed to be. But if you did that, you would end up with very little contact, very little preload, and a weak bolted joint. There are going to be some viewers out there our special group of engineers who will say, ah, come on. They'll say, we'll get those special surfaces machined super square so the gaps won't be that big. We'll write an assembly procedure for the tightening of the screws, and whatever gaps exist, those will close up when we tighten this thing together. Maybe. I'm sure people get away with this every day, or they think they're getting away with it, but it's a bad design, and you shouldn't do it. It will create frustration on the assembly line. I'm not sure these gaps will be that small, and if they are, it's only because we make tight perpendicularity callouts. And this gray part, it looks pretty stiff to me, especially in the direction of this giant rib. I'm not sure it's going to be very compliant at all. But anyway, let's have a look at this drawing. This is GDTG 00543. This is the way I bet 95% of designers would handle this drawing. Looking at the two surfaces, I kind of randomly chose this one here as being the datum A feature. They're both the same size and perform the exact same function, so it's not much of a choice, and it's a bad sign for us GD&T wise. I relate the side surface to datum A with a perpendicularity, and I call it my datum B feature. And let's make a note that whatever we put for our perpendicularity callout here, that's your gap. The only way to close that gap is to make this perpendicularity tighter, tighter, tighter. Okay, and then the holes that go this way, I reference with datum A primary and datum B secondary. And then the holes that go the other way, I reference with datum B primary and datum A secondary. But this is kind of crazy because both of these surfaces are acting as primary datum features. Another bad sign for us. Because there aren't two separate mounting arrangements for this part. There's only one. Those datum references I just showed implied that there should be two separate inspections for these hole locations, maybe using a gauge like this. On this gauge, this surface would be a primary datum simulator, and this surface would be a secondary datum simulator. And then it has these special holes up here on the primary datum simulator. So we place the part on the gauge to where it has full contact with the primary datum simulator, and then slide it over until there's contact with the secondary datum simulator. And then we check the hole locations with some special hole locator pins. Okay, and then we do the same thing on the other side where there's a separate inspection. Put the primary datum in contact, slide until contact on the secondary datum, and then we do the hole locator pins over here. You'll notice that at no time do we check the position of all 8 holes simultaneously. They're considered two completely separate interfaces. But if you don't like that, then this drawing, GDTG 00544, might be a little more correct. This one is similar in how I established datums A and B, but then I use them as equal precedence primary datum AB, and I reference that for all 8 holes simultaneously. In the inspection, you would have a gauge that simulates both datums and can check all 8 holes at once. And then if you ended up with gaps like this, the standard would instruct the inspector to slip in shims of equal thickness to neutralize the position. At least that's my interpretation. Usually when you have these equal precedence datum features, they are coplanar, coaxial, or at least like parallel to each other. This one is like folded around a 90-degree corner. We can hope that everyone is going to interpret this the same way, but will they? Anyway, I feel like with this drawing, we resolve one of the lesser problems. The bigger problem remains that our design is over-constrained and probably will not work very well in assembly. And I think that the drawings and the GD&T point to some signs that we're in trouble. And we're going to see some more of that as we move along here. But what are we observing about over-constraint at this point so far? Well, what I'll probably tell you at least a few times in this video is that over-constraint creates conditions in which there is no acceptable tolerance, in this case, the perpendicularity, and so we end up with multiple unsatisfactory mounting positions. And to overcome these problems, we have to distort the parts, stress them, force them to come together. And since we're always talking about constraint and degrees of freedom when we talk about datum features, it is in the constraint where we're really going to see the problems. And it's how we're going to fix the problems. Because once you get into the GD&T mindset, you're going to see these things right away and you're going to want to fix them. And then you're just a short step away from being everybody's favorite designer. Believe it. So let's look at another version of this brace with a more traditional bolted joint. In this one, all the screws are entering in the same direction. And just as a side note, this might be a double good thing because depending on how big this blue part is, it might be pretty difficult or require some special equipment to drill and tap holes on the end of a really long part. Okay, but I digress. In the last design, we were concerned about having screws in shear. In this design, we're dealing with that problem by having a close-fitting locating feature to limit the amount of slip that can occur and to keep the shear load off of the bolts. The drawing, GDTG00542, is pretty straightforward, I think. We have a 2x coplanar datum A surface feature. And then our locating feature, this undersized half-inch key here, becomes our datum B feature. And then all of our holes and everything are located referencing datum A primary and datum B secondary. Now look, even with this, there's still the possibility or even the likelihood of there being gaps. And that all happens here in this 5/1000ths coplanarity. There could be 5/1000ths gaps. But I feel like I can ask for 5/1000ths coplanarity here. I wouldn't want to ask for 5/1000ths perpendicularity on the other part. This is a simpler coplanar feature. It can be all made in one machining setup. And I have a couple other reasons for some confidence too. I think this is going to sit fairly evenly, etc. But anyway, I feel a lot better about closing a 5/1000ths of an inch gap than closing a 15/1000ths of an inch gap with screws fighting each other from two different directions. Some of our special over-constraint loving viewers will look at the small amount of gap in these locating features and think, I don't like that. They'll say, you know what I want is a little taper in these parts to force like an interference between the gray and the blue. And then if I do that, there'll be no slipping or shifting at all between these parts. Okay then, so to look at a drawing for this, it would be GDTG00545. We've got the same 2x datum A surface feature. And then in the detail, we can see our taper feature is dimensioned 500/1000ths at the root. The profile tolerance is unequally disposed. That's the circle U, with 2/1000ths being on this side, the outside of nominal, like we're trying for some kind of transitional interference fit. Now to me, this is a tight tolerance. It's analogous to plus or minus 3/1000ths. It's not just the profile or the form, it's like the straightness going in and out of the page across the entire width of the part. But even being such a tight tolerance may be so tight that it can't be made reliably. Will it ever be tight enough to get what we want? We'll get to that in a minute. But first, here in the hole position tolerance, we're using datum A as primary and datum B as secondary at RMB. Datum B is our taper feature, so by saying RMB, there's some more evidence that we're using this as an interference feature. So now look, datum A is a 3 degree of freedom primary datum, a planar geometric counterpart to these two surfaces, 3 degrees of freedom. Now, if you had this taper feature fitting into its idealized geometric counterpart, taper into taper, that would be a 5 DOF datum feature. If the taper feature is made small enough that there's clearance to the next part, then it could be a 2 DOF secondary datum feature at MMB, sure. But then it wouldn't be a whole lot different from the non-tapered clearance locating feature from GDTG 00542. Harder to machine, harder to inspect, but to be charitable, probably a little easier to put together at the instant of assembly. But what if the taper feature is made too wide? or if the tapered slot is made too narrow. It seems like this is almost what we're aiming for, with the tolerances pushing us towards interference. If it's like this, we're not even using the datum A surface, right? But maybe the idea is we're going to tighten these screws a whole lot, we're going to close this gap, and we're going to displace material around the taper. Well, this is a lot of planar contact, and even a couple thousandths of interference could be very difficult to displace. This seems to assume a high level of ductility of the materials. Maybe it could be done with some kind of a press. I'm sort of skeptical you could get it done with the screws. Probably would mess up the threads. You would have to tighten this up super evenly with the screws. It's not good. But some engineers, the kinds that weren't happy when this was a clearance feature, they just love interfaces like this. They force the parts to their will. And so they'll come back to this again and again. And I have more examples to show you of how I've seen it. And I used to do a lot of this stuff myself. But surprise, surprise, I think GD&T straightened me out on a lot of it. This whole thing with the datum reference frames, where we're always talking about 6 degrees of freedom, a primary datum that constrains more than a secondary datum that constrains more than a tertiary datum, it's a good system. Because if things work in theory, then we have a fighting chance of them working in practice. If I have a primary datum feature that constrains roll and pitch and translation, and a 2DOF secondary datum feature that constrains translation this way and yaw, then I have a path to setting these other tolerances, making them reasonable, and being pretty sure that these parts are going to go together readily every time. But in the case of GDTG00543 here, if I have 2 features, each with equal claim to being the 3DOF primary datum feature of this interface, fighting with each other, I guess, over who constrains rotation about this axis here, like this edge, well, you're asking for trouble, I guess, is what that is. And so your only course of action is to tighten this perpendicularity, which never actually resolves the problem until it's 0, which you can't get. All right, and there's a common thread here with the part GDTG00545. If I constrain 3 degrees of freedom with the primary datum, and then the way I'm using this, constrain 5 degrees of freedom with the secondary, I'm worried right away that we're going to need very tight tolerances on this taper feature in order to get the right amount of interference. And I'm worried it's going to be a lot of stress on the part. And I'm worried that the flat surfaces are not going to come together right. On this part, this almost seems like something we're doing to ourselves on purpose. For this one, I'm thinking, maybe it's just an accident or inexperience. But there's also something of an urge that all of us experience more or less strongly, a compulsion towards overconstraint. My goal for you in this video and in the next is for you to recognize overconstraint and to learn how to avoid its worst consequences. We'll get into some more examples and explore the topic more thoroughly in video 2. Thanks for watching.